Welcome to today's Feed Talk. We are going to have a presentation by Gilberto Goracci, who is a research fellow at Philip about downscaling water storage grids from simulated NGGM and MAGIC data. So no further delay.
Thanks, Jonathan. Hello, everyone. Sorry for being late. We had problems with the security. So a little bit quick introduction. Who am I? I'm an internal research fellow at the Explore office here at the Philip. Started this January, and I mainly work on hydrology, super resolution, and data simulation. My career is a little bit varied. I did a bachelor and master in physics and astrophysics, and then a PhD in space science, working on space systems and autonomous navigation of small satellites. So let's talk about my main project that is based around ESA's next generation gravity mission, NGGM. So with this mission, what we want to do is measure mass change in Earth system, and this comes with a very, very broad range of applications, going from ice sheet monitoring to change in the geodesy of the planet to especially hydrological applications such as forecasting of extreme events or land and groundwater or monitoring of the oceans. So the measurement concept of NGGM is basically we have two satellites working in a pair, and we have a laser to measure the distance variation between satellites and accelerometers to measure the non-gravitational acceleration. With this particular configuration, we aim at extending and improving the time series of the satellite gravity mission with much better spatial and temporal resolution with respect to what we have now with missions such as GRACE and GRACE Follow-On. We also want to reduce the uncertainty and the latency, which is crucial if we want to monitor extreme events, for example, because we need a very short latency from where the data is collected to when the data is available to the community. So the ESA-NASA collaboration on MAGIC here is a concept mainly based on two pairs of satellite. So we have the first pair, which is GRACE Continuity. So basically, it's a program developed by NASA and DLR. Works in a near-polar orbit as a global coverage, while the ESA mission is the NGGM pair, which will be sent to space in an inclined orbit and will improve a lot the monitoring of the gravitational field variation. The joint combination of these two pairs is the MAGIC constellation, and we expect at least 4 years of combined operation of GRACE-C and NGGM, hopefully starting in 2032. So let's say that the joint constellation of these two pairs will provide us with higher resolution products, shorter latency, and also, most importantly, higher accuracy for new science applications. So let's talk now about the terrestrial water storage. Terrestrial water storage is a crucial indicator to monitor the global water cycle and basically represent the total amount of water that we can store on and below the Earth. There are four main components, which is land surface, groundwater, soil moisture, surface water, and ice. The groundwater is the most dominant component in the terrestrial water storage. Satellite gravimetry is important because it gives us the only direct space-based measurement of terrestrial water storage on a global scale. Removing the non-hydrological signals like Earth deformation or atmosphere, is it possible to have an estimation of how the terrestrial water storage changes over time, so the terrestrial water storage anomalies? We normally measure TWS in millimeters of equivalent water height, which correspond to the height of the column of water needed to induce the given gravitational variation. So why do we need to downscale terrestrial water storage? The available data that we have limited spatial and temporal resolution. So we are limited by the 300 kilometers of resolution from GRACE on a monthly frequency. So we really are hiding phenomena happening at basin, sub-basin scales, because of course 300 kilometers are a very coarse resolution. Now, with the new constellation, things will hopefully change, because the NASA DLR GRACE-C will ensure continuity and global coverage. So we hopefully won't have data gaps from GRACE and GRACE continuity. But the main contribution will be provided by the NGGM pair, which will contribute to more than 90% of the mission performance over the areas below 70 degrees. Because as you can see from the pictures, from the picture on the right, GRACE-C will be responsible of the polar, let's say, the polar region, while under 70 degrees of latitude, we will be covered by NGGM, and those regions are the most relevant for hydrological application. So in total, with the joint combination of the two, with MAGIC, we will hopefully have 5 daily gravity field products with a resolution of approximately 200 kilometers. So in this work, in this topic, we try to downscale the level 3 products from GRACE-C, NGGM, and MAGIC, given by end-to-end simulations conducted in the frame of ESA studies, from 3 degrees to 1 degree of resolution, using AI frameworks like convolutional neural network and auxiliary meteorological data. So, how do we process this terrestrial water storage data? So, the framework of this project is the ESA-Sync project end-to-end simulations. So basically, these products come from the hydrology, ice sheet, and solid earth layers of the ESA Earth System model, which are then combined with ocean tide errors, the aliasing error, and instrument noise estimated from to be expected from the missions. And we have 3 mission scenarios, so the GRACE-C, NGGM, and MAGIC, with a temporal coverage ranging from 1995 to 2006. We have different simulation types, different spatial resolution, and different products. What we will use in this work is the high frequency, so 5 days of temporal resolution, and a degree order of the spherical harmonics coefficient of the gravitational field of 70. This corresponds to 2.7 degrees, so more or less between 200 and 300 kilometers. We can operate at different levels of data. Mostly we will work with level 3, but just to be coherent, a first introduction of the level 0 and level 1. So from level 0, we have basically the telemetry of the instrument, while level 1A and level 1B start to be calibrated and geolocated data. And then we will see now the products from level 2 onwards in the presentation. So here we have a more detailed overview. So we will work with the level 3B. B means that they are filtered data, so the one highlighted in the red rectangle, while the level 2 products are given in terms of spherical harmonics, while level 2P and level 3 are already provided in equivalent water height grids. So this is a first preprocessing measure that we apply. So the gravimetric satellites cannot measure the C20 term because it is a global deformation of the Earth gravity field, which is not, it doesn't produce local variation. So we cannot detect it with satellite to satellite tracking. Instead, we replace this term with measurements coming from satellite laser ranging estimation. Now, the impact of this coefficient is not so it's not evident at a first glance, but it's still not neglectable, and it's strongly related to the latitude of the pixel. Then we go from level 2P to level 3, correcting the glacial for the glacial isostatic adjustment, which is basically the slow rebound of the Earth after being compressed by ice sheet during ice ages. So when the ice melted after the ice ages, the Earth started to rebound, and we can still feel the effect on this. especially in regions such as Scandinavia and North America. As you can see from the pictures, you have at the on the left the GAI trend. Then at the central panel, you have the level 2P, which means uncorrected for GIA, and then the final level 3B products after the subtraction of this trend. And you can see that there are these patches, these blue patches, especially in North America and Northern Europe, which disappear after the correction. So now let's talk about the input datasets for the AI framework. We will use a set of climatological variables coming from ERA5 land dataset. So we are assuming that all of these variables are related with the terrestrial water storage. So all of these have an impact on the variation of water content. So we go from total precipitation, temperature, evaporation, soil water layers, and so on. And we also use the eTopo 2022 digital elevation model to have an overview of the altitude of the regions. Of course, these data are provided in a much higher resolution than what we need. For example, ERA5 comes at 0.1 degrees and at hourly samples. So we have to aggregate them both temporally and spatially in order to have products of 1 degree spatial resolution and 5 daily frequency. Then we have some pre-processing to do. So first, we masked out the oceans because our simulations are not comprehensive of the oceanic region. So we don't want to give that information to the neural network. So we masked out the ocean and consider only the land. Then we remove outliers, we normalize the data. And then there is a very important thing to do, which is to consider that the terrestrial water storage is a quantity that has memory. So what it means, the TWS at a given time depends also on past values of precipitation, evaporation, and so on. Because, of course, if it rains today, this will have an effect also in the future for the terrestrial water storage because the changes are not immediate, are not instantaneous. So we consider a 3-month delay for each dynamic variable. This corresponds to 18 5 daily time step plus the value at time t. So this brings us to a very high number of input channels that corresponds to 212, where the number of we have the number of dynamic variables, number of time sample, number of static variables, which is only the digital elevation model, and 2 time-related variables given in terms of cosine and sine of day of year. Here you can see a snapshot of the first channel of each variable, of course normalized already, because as you can see here, we have a skin temperature that goes from -2 and 1. You don't want to, of course, we don't have -2 Kelvin in Africa. Actually, we don't have -2 Kelvin anywhere. The last image is the digital elevation model, and the time information is given as grids in which the value of each pixel is the sine or the cosine of the day of year. The choice of cosine and sine is based on the fact that we want the time to be a continuous variable. So if we use, for example, the day of year, like from 0 to 365, then your network sees something that is linear, and then all of a sudden it goes to 0. And AI framework don't like something like that. So the downscaling strategy, mainly we have 3 approaches to the AI-based downscaling. The first, the simplest one, is the low to high approach, in which we train a model in a supervised way using the satellite products at the coarse scale, and then we use this model to predict at the fine scale. Of course, here we are making this very, very strong assumption that the relations at the coarse scale also are valid at the fine scale, which is almost never the case. Then there is the hydrological model approach, in which we train a model using the high-resolution outputs of a hydrological model, such as water gap, for example. But this means that we are training the model to mimic the hydrological model. So if the hydrological model is a very good representation of the reality, of course, your products will have will be a good representation of the reality. But if the hydrological model is not a very good representation of the real world, of course, you are training the model in the, let's say, in a misleading way. Then we have the eye-to-eye approach, in which we train the model to predict a map that is already at the high resolution. We upsample it at the coarse resolution, and we compare to the satellite product. So this is probably the most coherent way. However, the relations between inputs and targets at the fine scale are, of course, difficult to learn because we don't have constraint at the final scale. So the only term in the loss function that we have is the difference between the upsampled map and the satellite. Here we use a unit convolutional neural network, which is mainly composed by two parts. So we have an encoder in which we increase the number of features, but we reduce the image of the size of the image in order to compress the information and have so that the model learns, let's say, the features at all the levels of the image, from the, let's say, from the large scale to the local scale. Then we have a decoder part in which the network tries to reconstruct the final image, extending the dimension back to the original and shrinking the number of channels to one because it's only the TWS at the finer resolution. So this is the approach. So we have our high resolution inputs. We give them to the model, and we get a high resolution output. Then we upsample this high resolution, getting something that is now at 3 degrees. We compare this product with the target, that is the product coming from the satellite. We compute a loss that in this case is the mean square error loss. So we have the mean square error of each pixel. And then, based on this loss, we try to minimize it with backpropagation and update of the weights of the neural network. So here is a visual representation of what you expect to see. So the first image is the reference, so the ground truth coming from the simulations. It's very important to stress out that the reference is never seen or used during the training. So here we are doing an unsupervised learning. Okay, this is very important because in the real applications you won't have a truth of the terrestrial water storage. The first image that you have is the downscaled product, so the output of the network, which is then upsampled to the third image and compared with the TWS from the satellite. As you can see, at the satellite scale, the training is supervised because your target is the satellite. So you can see that the upsampled version of the output of the model is very close to the satellite product. The difficulty is to have something that makes sense and is coherent at the finer scale. So let's see some results. So we decided to focus on 5 regions, Europe, Africa, Amazon, the Ganges, and the Mississippi, because those regions are the, let's say, the most relevant in terms of hydrological signals. So we are interested in regions in which actually we have changes in total water storage. So we have a very strong influence in terms of hydrology. A separate unit is trained for each region, so we don't develop just one global model, but 5 smaller models. This just because it's easier for the computationally, and because in this way we can grasp the, let's say, the regional characteristic of each macro region. This is an image of the input gradients. So basically, this is something that you do to understand how much each input influences the final output of the network. As you can see, the biggest contribution comes from these volumetric soil water layers that, this is expected and this is correct because these layers are a direct component of TWS together with surface water, groundwater, and ice or snow. Of course, the main contribution to terrestrial water storage comes from groundwater, but groundwater is not a part of the inputs because it's not, from ERA 5, we don't have direct measurements of the groundwater. So this is one of the snapshots in the time series for Africa. So let's start from the comparison between the ground truth at 3 degrees on the left and the satellite products on the right. The first thing that we can see here is that the satellite product from gray sea is much poorer than the ones that we get from NGGM and MAGIC. And this will have an effect also on the downscaling. Because if you look now at the comparison between the high resolution ground truth and the downscale product, you see that the top picture, so the gray sea-like downscaled, is actually very, let's say, very messy. It's not very clear. It's not very. It has not a very high quality compared to NGGM and MAGIC. This comes from the fact that the original satellite products from NGGM and MAGIC are better. So here you can see that the downscaled image is upsampled back to 3 degrees and compared with the products from the satellite. And here, this is what I was mentioning earlier. So there is quite a huge difference between the products coming from GRACE and the one coming from NGGM and MAGIC. For example, there are these blue signals in Madagascar, or here the region this region in the bottom right part. So as you can see, NGGM and MAGIC are much better in retrieving high frequency, small scale structures. So this is the situation for Amazon. Here you can see that the same applies also to this region. So the data coming from GRACE is poorer, and also the downscaled product have a worse quality. In Europe, you can see mainly that in the Alps and in the beginning of Scandinavia, there are this very strong this strong signal that is reproduced in MAGIC and NGGM, but not in GRACE, even in the downscaled product. Then the same applies to Ganges and Mississippi, as we will see in a moment. And of course, also in this region, the signal from GRACE is much more attenuated, and you cannot reconstruct some of the structures. And in Mississippi as well, as you can see from the pictures. So now let's talk a little bit about the metrics. So let's quantify this, the model's performances. So here we compute the spatial correlation in terms of Pearson R between the ground truth and the downscale product. So this is the correlation with the reference at 1 degree. And we can see that the NGGM and MAGIC, so here the results are divided by region, results from NGGM and MAGIC provide much better spatial correlation than GRACE C, due to the much better satellite products. Here we can see the correlation between the unit low resolution, that means the downscaled product upsampled back to 3 degrees, and the satellite. So this is the correlation with the reference at 3 degrees. What does this mean? That the downscale product matches the satellite at the coarse scale. So there is no loss of spatial coherence. This is very important because when you try to improve the resolution of a given product, the first thing that you want to avoid is that when you go back to the original resolution, your product is worse than the original. And unfortunately, this doesn't happen in this case. Then we computed the variance ratio and the low-pass structural similarity index measurement. So the variance ratio tells you how much the model is able to reconstruct the variance of your reference field. Basically, and at the same time, the structural similarity index measure tells you how the, let's say, the structural properties of the map are preserved in the process. Here, what you can see is that the variance ratio is much higher for NGGM and MAGIC. This means that when I say higher, I mean closer to 1, because basically it's the ratio between the variance of the downscaled field and the variance of the reference field. So in case of a perfect variance ratio, you would have 1. And at the same time, you have a higher structural similarity index for NGGM and MAGIC, outperforming GRACE C-like. Low pass means that we want to, let's say, first we apply a low pass filter in order to evaluate only the, let's say, the large scale structures of the image. Now let's take a look at the trend. So the trend basically evaluates the long-term behavior of a given quantity. In this case, the trend tells you basically if the region is losing water over time or gaining water over time. In fact, the units are measured in millimeters per year. So the blue regions counterintuitively correspond to a loss of water. So if a region is deeply blue, it can be at risk of drought, while if you have very intense red region, the terrain is gaining water, so it can lead to floods. As you can see here also, the first row is the reference, while the second, third, and fourth are the products. And here as well, you cannot retrieve information using GRACE, while you can still reconstruct some higher frequency features from NGGM and MAGIC. And the same, as you can see here, highlighted the region highlighted in the red circles. And this is true also for the residuals. So basically the error between the trend and the reference trend. Here the errors are much lower for NGGM and MAGIC, especially at the center of the African region and in the Brazilian region in Amazon. And here we can see it in a quantitative way. So we have a reduction of the errors going from GRACE, C-like, and NGGM, both in terms of root mean square error and mean average error. And so one thing I want to stress out is this is different. We use more metrics for the error because they have a different, let's say, they give a different weight to the outliers, because when you do the root mean square error, for example, the outliers are weighted more, while if you compute the median average error, the mean average error, we have a less contribution from the outliers. So it's important to have an idea of both of them. So wrapping it up, we addressed the downscaling of the simulated GRACE data using AI. And we worked with filtered 5-daily level 3 data from end-to-end simulations using auxiliary data from ERA5 Land and the eTopo digital elevation model. The downscale products are compared to the HIS reference from the ESA Earth System model on 5 regions of interest. So we have high temporal correlation with the ground truth for all mission scenarios. This means that overall, how the TWS changes over time is coherent with our HIS reference in all the mission scenarios. We don't lose structural coherence at the core scale with respect to the reference and the satellite. As you can see from the picture, we have a downscaled product upsampled to 3 degrees, which is almost identical to the satellite product. But at the same time, we have the retrieval of some high-resolution structure at the fine scale, as you can see from this image of Africa. And finally, the downscale NGGM and MAGIC outperformed the downscale GRACE continuity due to the much better satellite products. And you can see here in the last column of the table, the improvement going from GRACE to MAGIC. So the variance ratio, for example, has an improvement of 47.4%, and the errors are reduced, and basically all the correlation and structural similarity indexes are much better. But of course, this approach has some limitations. So the main limitation that I want to stress out is that here we use the ESA Earth System model 2.0, which is forced by ERA interim and the LSDM hydrological model. So our simulated world is made by ERA interim. ERA interim now is not available anymore. So we are trying to reproduce the terrestrial water storage using data from ERA5. So we are trying to, let's say, we have data coming from different sources. And this is not really, it's not the best, let's say, conceptually. So this will be hopefully fixed with the ESA Earth System model 3.0, which will be driven by ERA5, and LISFLOOD, which is a newer hydrological model. So we can use the same input data sets both in the simulated world and in the AI approach. Another important thing is that if we use pixel-wise metrics to assess the performance of this method, they are often unreliable because they are very sensible to small shifts or misalignments. So if the network tells you that there is a river in a part of the map, but then this river is shifted by just 1 pixel with respect to the ground truth, your pixel-wise error gets incredibly high, even if visually you are reconstructing something that is good. So it's difficult to evaluate globally the performance of the unit with a single metric. Then, talking about future developments, of course, we want to test the approach also on filtered products to see if we can have an alternative way of filtering the data, or if we can skip the filtering, which is a very complicated process, and still have higher quality downscaled products. And we also want to include uncertainty information, because this is one of the big limitation in general of AI frameworks compared to standard data simulation systems, which always provide you also like a covariance matrix or some information of the uncertainty, which we don't have in this case. Then, of course, we can do some hyperparameter tuning and optimization of the architecture of the neural network, but this is more on the technical part of the AI framework itself. But most importantly, we want to introduce some physics-based terms in the loss function in order to have something that is also physics-driven and not only data-driven, because at present time, we don't have a constraint at the high resolution. So we only have the comparison with the satellite at 3 degrees. And what happens below that resolution is all driven by the data. And of course, one can test other frameworks like transformers or foundation models to hopefully improve the performance compared with a simpler model like a convolutional neural network. So with this slide, I conclude, and I thank you for your attention. And please feel free to ask any question, both from the live audience and the online audience.
Thank you very much, Gilberto, for the talk. Does anyone have a question here from the audience? I had a question, but I forgot. Do you have any intuition that how your predictions and their quality would change if you go? I mean, I guess it's always the impossible question to answer, but from the simulated data to the real data?
Oh, yeah. I have the results on real grace. I've already done the, but you have no ways of validating it.
Yeah.
Because if you try to you cannot compare the data that you get, for example, with in situ measurements. It's very difficult because they have strong biases. And also like groundwater wells, for example, they give you the absolute value of the water, while what you measure with grace is the variation. So you would need to have a very good time series of measurement. It's complicated. And this is basically the intrinsic problem of the hydrological downscaling. So you get a result, but if you, in the real world, you have no way to be sure that what you get is right or not, because you have no higher resolution ground truth. So we can only say that if in the simulation world the approach is coherent, since we are not mixing the two words, because either we use only the simulation or we use the ERA 5 plus the real data, you can only say for like transitive property that it will be coherent also on a real data, but there is no like analytical way to assess it exactly.
Yeah, that makes sense. It's a tricky problem.
Usually what you do is trying to analyze like the spatial correlation and at the coarser scale. So you want your products to be coherent with the satellite. And some approaches basically compare the downscale product with the model, but of course it has also some limitations. So it's very like kind of a gray zone to be in.
Yeah. There is a question in the chat.
In the chat, or do you
whether you could whether you have some insight on the different contributions of the variables to the model predictions?
Yes. Let me go back to the slide. So basically, the most important. Okay. So here you can see each bar is a sample of one variable, and every color is a variable because, as I said, there are different time steps for each variable. They all contribute more or less the same. So here you have total precipitation, here you have temperature, skin temperature. This one is surface pressure, which is like the least important. Yes. Yeah, they come out. What? Repeat the color. Let's say the purple one is the surface pressure, which is the least important one. The most important are the volumetric soil water, because they are actually a direct measure of water. So those are, thankfully, the most important. And then you have a good contribution from the time information, which can be due to several reasons that we did not investigate. But the thing here is that it's important that the volumetric soil layers have the dominant contribution.
What is the pink and the slightly less pink?
This one?
No, to
here.
Yeah.
So okay, so they're all layer. The first one, the brown one, is the layer from 0 to 7 centimeters underground. Then yeah, and of course, since in general the TWS is driven by the groundwater changes, the more you go in depth, the more the component. This is not the groundwater still, because the groundwater is much deeper than that, but still the layer from 1 meter to 3 meter is more contributing.
Okay, interesting. And Manu asks, just good grace downscaling products be used to estimate large dam reservoir variations?
Hey, this is a tricky question. This is the next step of the work. So what we investigated so far is to have an estimation of, for example, drought potential index or flood indexing, to have a risk map of these kind of events, using both the original products and the grace and the downscaled ones. And we actually noticed that there are some events that are recorded in the history that are much more evident in the downscaled products than in original ones. So in principle, yes, they could be of help if you want to use this data for the actual applications. However, before doing bold statements, I think that it's important to have an idea, to have an uncertainty measure associated to our downscaled products, in order to to know if what we are using for the applications is correct or not, just to be scientifically more coherent. But in principle, yeah, we are doing this because then we want to use the new products for the applications.
Well, another question is, someone in the chat asks if you could summarize again the problem setting. They say MAGIC will start in 2032. So this experiment was done with simulated data. Will it deliver data in 3 or 1 degree resolution? I guess they mean both the mission and your solution. And was this an H2H type of model?
Yes, H2H. Yes. Can you repeat the data? The 3 and 1 degrees?
Will it deliver data in 3 or 1 degree resolution?
No, you mean the actual mission? If you mean the actual mission,
yeah,
the actual mission will be around 200 kilometers, so around 2 and something degrees. But of course, it will depend. It will still. It's not certain. There are different frameworks for the simulations, and all of them give you products with a slightly different resolution ranging from 3.5 to 3, something like that. In our case, the exact resolution is 2.7, sorry, which we approximated to 3 degrees for simplicity. But we won't have the data at 1 degree from the satellite. So this is just now in the simulation we have it because our Earth system model can give you data up to 1 degrees. And this is also why we don't go deeper than 1 week. In principle, we can also go to 0.1 degrees or 0.5. The problem is that our reference only goes up to 1 degree resolution. So if we go below that, we have no ways to validate it, basically.
Okay, that makes sense. Thank you.
I didn't get why you're applying a low pass filter. It was measuring the SSIM. Why you're applying a low pass filter? You need that the bit.
Just to, let's say, let me go back to the because what you want to see here is the overall structural coherence of the image. The problem is that if you apply a low pass filter, you are basically excluding the possibility of having very high outliers, which can happen with AI. So you want to just if you go higher frequencies, you get the, let's say, like small rivers, something like that. Well, if you apply a low pass filter first and you evaluate the rest, you are basically only consider the overall structure of the field. So this is what we mean. But you can also, like, if you want to evaluate the ability of the network to do the opposite, you can also apply a high pass filter, and then you are left with, let's say, high frequency variations. But in that case, you are much more subject to like outliers driving your error crazy. It's just a matter of what it's not something. It's not written in stone. It's just something that it depends on what you are looking for with the MAGIC.
And to do the downscaling, so you train different units for each region. Yes. You compare to a single unit, or did you try to like train a global?
You can. The problem is that so I mean, in principle, you can even have a single model that process the images as a whole, because in the end you're working with a 3060 times 180 image. So in principle, it's doable, but computationally is kind of slow. So you would need like to divide the image in patches and a different kind of approach. We started with that actually, like with a global model. The problem is that it's not convenient because, like, if you look at the map here, at the global map, like, but most of the time you would be looking at region you have no interest in, because like if you look, there will be patches only made of oceans. You don't need it, or you don't need to know what happens like in Greenland or at the poles. So there are regions which you are interested in, and mainly these 5 or some like slightly others depend on what you're looking for. But you can go global, but doesn't give you like a very more solid use case. I mean, there is no advantage in going like have a single global model than 5 smaller ones. So, but in principle, yeah, of course you.
But then we're wishing the opposite. What if you, instead of just 5, you go more instant? They use 10 units, one for
you can of course, and the problem in that case could be that you will be working with very small images. Like, for example, this unit is limited to 2 shrinking layers, because we start from a mirror just that is 48 times 48. So when you arrive when you divide that by 4, you're left with a 12 pixel. So if you work with even smaller images, then after 2 layers, you are left with something that is like 2 pixels times 2 pixels. And in principle, you can, of course, but it may give you like stranger results because you're basically almost working like pixel wise. That's the only, let's say, limitation, but in principle, yeah, it's feasible.
Do you have any indication or thought on what is causing like the errors? So sometimes in the plots with the difference between the prediction and your reference data, you have bias like regions that have a bias that is like structural. No, that is not just a noisy error, but there is some that clearly have a positive or a negative error. But do you know what could cause this? Or
Okay, yeah. For example, I don't show the satellite here, but this region here is even in there are some artifacts also in the simulation product in the ground truth. This happens also in other areas, which can kind of mislead the network, and you are left with this like very strange patterns. And also like this is a little bit harder to say because this is the trend, but maybe I have some spare slides on the error.
Yeah, sorry. I think I was also confusing your plots a little bit. I'm sorry.
Why?
Yeah, because you're not actually showing the error. It's actually the prediction. So
no, I mean here is the errors in the residuals, but the problem is that those residuals are from the trend. So from the trend, you have to consider the whole time series, and then, but no, they have a kind of, well, for example, here, you see that there are this kind of stripes, like going circular. This comes from artifacts in the simulations. You also have those in Europe, but. I would say they are mostly, even if they don't look like that, I would say it's mostly noise. Because, yeah, from what you can see from the error plots of the single touch snapshots, the error is mostly noise, let's say.
okay.
Maybe we can also, like from here, I mean, we cannot say much about the errors because we don't have a plot of the errors, but no, it's really, maybe when you have stronger signals, you have higher errors as well, because it's difficult to reconstruct the exact amplitude, and it's also more evident in the plots, and also depends on the color scale that you're using.
Okay. Someone online is asking also about the region. I think the regional split. Why are you making new regions, and why are you not following the Cordex setup? I don't know what Cordex is.
For simplicity.
Okay.
Nothing, no particular reason, just I wanted something like, say, as simple as possible to divide the regions using latitude and longitude. Also, I want to be working with 48 times 48 pixels regions wide, just for convenience. So it doesn't really matter how you, I mean, as long as you include the regions with most relevant hydrological signal, then the exact division is not important.
What is the Cordex setup? Do you know?
No.
I met model. I
think it's a model with like boundaries and limits of each basin or sub-basin.
Yeah, this person shared a link. Okay. If no one else has a question, I think we can wrap up.
Okay.
So
thank you. Thank you very much. And of course, feel free to like ask and whatever. Okay, stop sharing. Thank you all, guys. Bye bye.